Hello and welcome to our continued journey through James Stewart's calculus textbook. We're in chapter 6, which is applications of integration. The fourth section is on work. Now, you may have had a physics course at some point. In fact, I suspect that Stewart assumes that you've had a little engagement with physics, which is unfortunate if you haven't. But we can talk through it. What is work? I think we have a kind of a popular sense of what work is. But in physics, we think of work as a force exerted through a distance. So let's say you have a really heavy box that you want to slide across the floor. So it's going to take a certain amount of force to push the box, and then you're taking it through a certain distance. I'm not sure that this is a perfect example, but it's helped me to remember that work equals force times distance. You're doing work on something by taking it through a distance. Now, there are other kinds of work, electrical work and so forth, that don't involve a distance per se, but the unit, when we're thinking of it as force times distance, it shouldn't be a surprise that the unit of work is the Newton meter, where the meter is a unit of distance and the Newton is a unit of force, named after Sir Isaac, of course. Another way of thinking of work is the change in kinetic energy. Kinetic energy is the energy of motion. So let's say something has X amount of kinetic energy and you do work on it and it goes, it has Y amount of kinetic energy. Then if you subtract, the difference between the energy it had when it started and the energy it had when it ended, that change in kinetic energy is another way of formulating work. And I should mention that the unit of joule is a joule is a Newton meter, but often it is more convenient to speak of the joule as the unit of work than it is to speak of the Newton meter. Now, of course, some other things that if you've never had a physics course, you may not know. So, for example, Newton had 3 laws, and his second law was that force equals mass times acceleration. So if you multiply mass times acceleration times distance, that's mad. Mass, acceleration, distance. Ha, 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 ha. Physics is funny, yeah? Calculus is so funny. But anyway, Newton's second law, F equals ma. It can be formulated in other ways. So, for example, force can be calculated as the change in momentum. But let's not talk about that right now. So that's a useful little tidbit to remember when doing work problems. To put that in calculus terms, force equals mass times the second derivative of distance, d2s d2t squared, where s is a unit of distance. So basically, the derivative of distance in relation to time is velocity. And the derivative of velocity with respect to time is acceleration. Velocity is the first derivative of distance, and acceleration is the second derivative of distance. Again, things that you may know by now, hopefully, if you've gotten this far in calculus. There's also something called Hooke's law that has to do with the amount of force. For example, if you've got a spring and you pull the spring and you put potential energy into the spring by pulling it out, and then you let go, boing, 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 then the formula for that comes from, I think it was Richard Hooke? F equals kx, where k is a spring constant. By the way, I have a video somewhere in the universe of YouTube. You can find it if you follow the links from this YouTube video back to my webpage. And then it'll tell you the link to the work video. I believe it was actually the very first physics video I ever did, so it's probably a little rough. I've developed, not that I'm much better, but I've gotten better, I think, as I've done a number of these sorts of videos. But I have a different video on work. I'm almost embarrassed to look at it, but it's out there in the universe, the YouTube universe. Okay, so what is work? In physics, it is force through a distance. Okay, and so we've got the tools now. Let's dig in. What if the force isn't constant? Well, that's of course where calculus comes in. You know, in high school physics, a lot of the time, you just learn these basic formulas that work fine because you're just assuming that the force stays the same throughout the distance. So it's not like you know, when I'm pushing the whatever, the box across the floor. But calculus comes into play when the force isn't constant. And so here's a monstrosity. So work is therefore the limit as n approaches infinity of all the little bits of force, all the little bits of force times all the little bits of distance. This is how calculus works, right? This is how integral calculus works. We add up the summation notation. We add up the sum of all the little itty bitty force distance moments. So there's a force distance moment, and there was a force distance moment, and there was a force distance moment, and eventually we get to where we're going. Zeno, of course, Zeno's paradox is wrong. I could tell you why using quantum physics, but I won't. Okay, so you add up all the little force times distance, force times distance, force times distance, and ta-da, you get the sum. And another way, of course, putting that in integral calculus is that work is the sum from starting point to ending point, from A to B, of the force times every little infinitesimal dx, every infinitesimal little change in distance, and times every, by whatever the force formula is. Let's assume you have a formula that tells you what the force is for, even if it's variable, you know, maybe it's a roller coaster force, you know, but anyway, you have some sort of formula, or you can break it up into parts where you, for this part, it had this formula, and for this part, it had this formula. But basically, here's the basic principle. The work is the summation of all the infinitesimal force times distance bits. Okay. And so you plug in for f of x, you plug in for the force, whatever is appropriate, ma or kx if it's a spring, and go from there. And there are 5 examples in this chapter. Some of them, the last ones deal with this integral calculus, where we have, for example, there's one with a spring. And I now am going to talk through example 5, which is the hardest of all the examples. With fear and trepidation, let us move forward with this problem. So this problem is basically, you've got some sort of liquid in a conical tank of some sort. It's a 10-meter deep tank, and the liquid's in it up till, it's water. Okay, it's water, as I recall the problem says. It's not filled all the way to the top, so it's 8 meters full, which means we have 2 meters at the top. The radius of this cone at the top, the base, it's upside down, but the base is 4 meters across. So how are we going to, so let's say we're going to drain this puppy. We're going to suck all this water out of the cone. How much work is that going to take? Well, let's freak out. Dun, 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 dun. Okay, so let's don't worry, we can do this. Especially since we've got the answers right in front of us. So how are we going to do this? Well, we think of these little cylindrical slivers, and of course, what is the area, or what is the volume of an infinitesimal sliver? Well, pi r squared h, if you remember, is the formula for the volume of a cylinder, and so h is basically little delta x, and pi r squared, r is wherever, ri means r wherever we're at in this thing. We know what pi is, we know what r is, we know what, okay, so we're good to go. Let's move on. So work is going to be basically the sum from 2 to 10 of fx dx. So from 2 to 10, so we're going from 2 to 10, 2 to 10. We could have done 10 to 2 and flipped it, you know, but we're going to go from 2 meters to 10 meters. Those are our A and B of the force times dx. So let's just write down all the formulas we know. F equals mg. Now again, he just assumes you know this, I guess. He assumes you've had a basic physics course by the time you're, you know, in this part of integral calculus. Maybe he doesn't assume. It would be wrong to assume that, probably. But basically, force equals ma. What G is the gravitational force, the gravitational acceleration constant, 9.8 meters per second squared. That's the acceleration on an object due to gravity when it's near the surface of the Earth. So G is just another way of saying A. And whenever we're dealing with a gravity issue, an up and down issue around the Earth, then the way we calculate the force, and by the way, the force in this case is basically the weight of the water at a particular point. So this is just F equals ma, where A is the gravitational acceleration due to gravity. Okay, what is mass? How are we going to find the mass? Well, mass is density times volume. Density is amount of matter per volume, and so if we multiply the amount of matter per volume times the volume, we get the amount of matter, or the mass. So mass equals density times volume, and it tells us in the problem that the density of water is 1,000 kilograms per meters cubed. Okay, so we're getting somewhere. We know what G is, 9.8 meters per second squared, and we're getting where we're getting to know what M is because we know what the density is. Now we need to figure out what the volume is. Well, as we just said, the volume is pi r squared h for each little cylinder sliver of this upside down cone. So how are we? So we know what pi is, 3.1415926535, and so forth. We know what h is, it's delta x. So now we need to figure out what r is. What is r? Since Stewart is very clever, he's going to find what r is by proportionality. So we know that the cone as a whole is 10 meters tall, and the radius is 4 meters across. And so what this little sliver is going to be, the height at any point, is going to be 10 minus whatever point of x we're at. And the r is going to be, whatever r we're at. xi and ri basically mean x wherever we're at and r wherever we're at. And so basically, using proportionality, 4 over 10 is r over 10 minus x. Ta-da! And now we just solve for r by multiplying, cross multiply, or you could just multiply both sides by 10 minus x, and you get r equals 4 times 10 minus x over 10, which is 2/5, 10 minus x, blah, blah, blah. Okay, now we've got it. We've got all the things we need to go. And so basically, volume equals pi r squared h. H is delta x. We know what pi is. And we just found out that r was 2/5 times 10 minus x. So if you square 2/5, you get 4/25. And if you square 10 minus x, you get 10 minus x squared. Okay, we got the volume. Times the density will give us the mass. So multiply this times 1,000 times the gravity, gravitational acceleration, 9.8 meters per second squared, will get the force. And so we multiply this by 9.8, and we basically get this formula. That the work done for any little sliver is going to be 1570 pi times wherever we're at in the x times 10 minus x squared times delta x. Now I did not do all of this for you. The rest of this involves some very basic integral calculus. But we go back to the original formula. We plug in this is the formula for the force times the distance, which is the same as basically, and we're doing it from 2 to 10, right? And so you can look at the book to see, and it comes up with this, which equals 3.4 times 10 to the 6th power joules, or meter seconds. But let's go with joules. And that's the problem. So this is a really short section, 3 pages. But this particular problem took most of the video. Work, yeah, those cars never seem to stop coming. But this has been a video on work for calculus.